For the second example, which is a rational inequality, we have x minus 1 over x squared minus x minus 12 greater than or equal to 0. In evaluating a rational inequality, we find the solution set where all the possible values for x are found. So in this case, we have x minus 1, and we factor out the denominator, we have x minus 4 times x plus 3, still greater than or equal to 0. There are 3 steps in evaluating a rational inequality, and I'm just going to write it down. So we have step 1, identify the polynomials. If we identify the polynomials, we will have an idea on how we plot the intervals, which is in the next step. So first, let's identify the polynomials we have for both numerator and denominator. So polynomials, as we know, are expressions that involves the use of variables or coefficients such as x. So in the numerator, we have x minus 1. In the equation, we have, in the inequality, we have x minus 1 greater than or equal to 0. For this to be true, we have x be equal to 1. For it to be equal to 0, x minus 4, which is also a polynomial, greater than 0, we have x equal to 4, and x plus 3 greater than or equal to 0. For that to be true, we have x equal to negative 3. So these values are what we will be using to create the intervals in the next step. So let's proceed to the next step. We have step 2. Sketch the interval line. Sketch the interval line using the x values we obtained in step 1. So we will be sketching a straight line. This one goes to negative infinity, and this goes to the positive infinity. So we have, on the left side, we have negative 3, negative 3. Then we have, say, our 1 here, and then our 4. Here lies all the possible values of x. So for negative 3, we evaluate the left and right side. So the values for its left side, which is here, are x values that are strictly less than negative 3. So this goes for negative 4, negative 5 to negative infinity. Note that we do not want to include negative 3 on our possible x value. Remember that our equation, rational inequality, was x minus 1 over x minus 4 times x plus 3 greater than or equal to 0. Now the reason why we do not want negative 3 to be included on our possible values for x is because if we put negative 3 here plus 3, which is here, that would be 0. And 0 times a number here would be equal to 0, and anything that divided by 0 does not exist, or it's an error. It's not included. So we do not include negative 3. So we write x strictly less than negative 3. And to remind us that it's not included, we draw a hollow circle. Okay? So for the right side of negative 3, we have x values that lies here. X values that are found between negative 3 and 1. So we have x that are greater than negative 3, but less than or equal to 1. So we want to include 1 to our possible values of x. So if we put 1 in all the x's in the rational inequality, the result would be greater than or equal to 0. So if that would be 1, 1 minus 1, which is equal to 0, the numerator would be 0 on the spot. So we have a rational inequality that satisfies greater than or equal to 0. So to remind us that the value 1 is included, we draw a solid circle. So for the right side of 1, we have x values that lie here. We have x values that lie between 1 and 4. So we have x greater than 1, but strictly less than 4. Note that again, we do not want 4 to be included in the possible values for x, because if we put 4 in this polynomial, for this x here, that would result to a 0 denominator, which is invalid. So we have x intervals here that are greater than 1 but less than 4. So for the right side of 4, we have x values that are greater than 4. So we have 5, 6, 7, 8 to 1000 to positive infinity. So now we have our intervals. So in the previous step, we obtained the intervals where the possible x values lie. So we need to narrow it down further. That's why we need to come up with a solution set where these x values definitely satisfy the rational inequality. We will ask ourselves if these x values make the rational inequality greater than or equal to 0. To do this, we will need an interval table, what we have here in step 3. So we have this very systematic interval table where we have the intervals as columns. So the intervals we obtained in the previous step was x strictly less than negative 3. We have x greater than negative 3 but less than or equal to 1, and x that is greater to 1 but less than 4, and x greater than 4. So in the rational inequality, we have x minus 1 as the numerator and x minus 4 times x plus 3 as the denominator. And together, the rational inequality was x minus 1 over x minus 4 times x plus 3. So let's complete this table. So the test point would be in the first column, we have x less than negative 3. So the test point would be anything that is less than negative 3. So for easier math, we say we have x be negative 4. Since we are looking for x that are less than negative 3. For this, our test point would be 0. 0 is less than 1 but greater than negative 3. For this interval, we will have, say, 2 as our test point since it's less than 4 but greater than 1. Here we have x greater than 5. So let's simply say that it's x greater than 4. So let's say 5. So these are our test points, negative 4, 0, 2, and 5. So go get your calculator and let's solve for this. So when negative 4 minus 1, in the numerator we have negative 5. For 0, we have negative 1. For 2, we have 1. And if x equal to 5, we have 4. And we have 8, negative 12, negative 10, 8. So if we divide these two, numerator and denominator, we will have negative 5 over 8. So is this greater than or equal to 0? No, it's not. We have negative 1 over negative 12, which is 1 over 12. Is this greater than or equal to 0? Remember that our rational inequality was x minus 1 over x minus 4 times x plus 3 greater than or equal to 0. So is this one greater than or equal to 0? Yes, it is. For this one, we have negative 1 over 10, which is this greater than or equal to 0? No, it's not. And for this 4 over 8, we have simply 1 over 2, and it is greater than or equal to 0, so yes. Now, for these values that satisfy the inequality greater than or equal to 0, these are definitely the intervals we are looking for. Now that we have the intervals we were looking for, which was x less than or equal to 1 but greater than negative 3 and x greater than 4, we now have our solution set in the form negative 3, 1, union 4 to positive infinity. So the possible values of x lie in this solution set. So notice that we use the square bracket here because of the less than or equal sign. This means that 1 is always included. So therefore, we have this as our final answer. And we would write, for formality, we would write, therefore, the solution set of the given rational inequality is negative 3, 1, union 4 to positive infinity.